Hello, my name is Richard Lobianco from Scottish Carbon Capture and Storage at the University of Edinburgh. I'm very happy to welcome everyone to today's webinar. This is the project's fifth webinar, and today's topic is the detailed development plans of two selected CCUS value chains for the Baltic and Mediterranean Sea regions. We have two speakers today, and they are Audrey Lopez from Genesis Energies and Leandro Enrique Sosa from Ramble. Without further ado, I would like now to hand over to our first speaker for the day. Audrey, the floor is yours.
Okay, thank you, Richard. Thank you very much for the introduction. So my name is Audrey Lopez. I'm working for Genesis Energies as a senior study manager and consultant, and I'm very happy to share the outcome of the work package 4 of the CCUS ZEN project with Leandro today. So I will first give you a very brief introduction or reminder of what is the project, and then I will focus on the results of the detailed plan developed for the CCUS value chain in the Mediterranean Sea region. I will also provide some highlights on the project risk assessment that has been carried out, and that can be also relevant for both regions. And then I will let the floor to Leandro to go into more details on the Baltic Sea region results, as well as the business model aspects. So let's go into the introduction to the project. So as you may know, the project is funded by Horizon Europe and started in September 2022. It is planned to stop and to end in January next year, with results which will be made available on the website of the project. The main objective is really to enable and to facilitate the development of CCUS projects in two regions, the Baltic Sea and the Mediterranean Sea regions, but also to identify potential new projects of common interests for the transport and storage aspects. That was discussed and presented actually in the previous webinar by Leandro. And finally, and it's the purpose also of today, to contribute to knowledge sharing and dissemination of the results. Before going into the details and the results, we wanted to highlight the fact that the scenarios which are presented and developed as part of the project, while based on obviously an industrial reality on the ground, they are forward-looking scenarios which are based on preliminary data and data available as of today to the consortium, so subject to further research and input data validation for next steps. However, it provides a good initial framework for the development that we are very happy to share. So the two regions that we are looking at, the Baltic Sea region, including Denmark, Sweden, Finland, Germany, and so forth. And in the Mediterranean region, we are looking at France, Turkey, Spain, Italy, and Greece. So the project focused on these two locations, started with a mapping of some technical aspects related to emission sources, like carbon emission sources assessment, transportation infrastructure identification, storage sites identifications, and in parallel looking at the different non-technical aspects such as regulation, governmental policies, public acceptance, etc. From these two first work package, the consortium was able to identify 4 value chains per region, meaning 4 for the Baltic and 4 for the Mediterranean Sea region. And through a high-level comparison and SWOT analysis, 1 chain was selected per region. And this is really the purpose and the objective of the work package 4 that we are presenting today, is to share the more, I would say, detailed assessments of the 2 selected value chains. The work package is led by Genesis and Technip, and we have mainly also been involved in the Mediterranean Sea region. Ramble with Leandro has been looking at the Baltic Sea region, and we have been supported by a number of partners such as Perspective, IOM Law, CO2 Value Europe, Accelera, BRGM, to develop the detailed plans for those 2 value chains. the last work package looking at the knowledge sharing and dissemination obviously has been going on throughout the full project. So that was just a quick reminder of the project and where we are today. So I will now share with you the focus on the Mediterranean Sea region value chain developments. So as I presented before, the first activities were associated to mapping the needs of emitters, what storage sites are available, so that you can see that on the pictures here. On the left, the different emissions and locations, and on the right you have in parallel the different storage sites which were identified. And by doing those two, in addition to the technical mapping, we also looked at, as I said before, the non-technical aspects. And by combining the two elements, the consortium identified 4 value chains that you can see on the right, which could be relevant for the Mediterranean Sea region. The SWOT analysis highlighted the fact that the Mediterranean 2 value chain involving a cross-border value chain between France and Spain could be the most relevant value chain to be detailed. So that's the one that I will detail further in the coming slides. Just one thing I wanted also to highlight is the fact that the project didn't want to do the same as existing projects. So in purpose, some of the possibilities were not considered, such as sending the CO2 to the Ravenna storage sites, for example, because we know that there are existing projects which are ongoing, and obviously there was no reason for duplicating existing activities. So that's why it's really the value chains which were identified are really focused on new value chains. Okay, so now let me go through the selected value chain. As I mentioned, this value chain involves France and Spain, with emitters located in 3 different clusters. One cluster around Fos-Marseille in France, and 2 clusters in Spain, one in Barcelona and one around Tarragona. So there has been an exercise to estimate the amount or the possible amount of captured CO2, which could be relevant and addressed by this value chain. So this assessment was carried out using public emission data from 2022, and assuming a certain percentage of implementation of CCUS amongst other decarbonization solutions for the different emitters. There was also an assumption based on the efficiency of the carbon capture technology. So using these different steps and assumptions, a value of captured CO2 which could be handled by this value chain was quantified. So a total of around 10 million tonnes per year, split between around 5.5 from Fos-Marseille cluster and 2.2 and 2 million tonnes per year from the Barcelona and the Tarragona clusters. The storage site, which has been selected and identified for this value chain, is a site located around 60 kilometers away offshore Tarragona. It's a new reservoir where an exploration permit application is ongoing, so it has not yet been appraised, but we have, through information from the BRGM, some assumptions that have been shared to be able to quantify the amount of CO2 which could be stored within this reservoir. And you will see a bit later the amounts, but basically the assumption was this reservoir could store around 200 million tonnes per year of CO2. In addition to looking at the capture, transport and storage, we also looked at CO2 utilization opportunities. The scenario is considering potential use as e-fuels, and that could be envisaged at each cluster. However, this application and this utilization pathways has some specific requirements, in particular related to the type of CO2, needing mainly to be biogenic to respect and to fulfill some of the EU regulations, and also is really dependent on the availability of green hydrogen at acceptable costs. So you will see later that even if those opportunities have been identified, the detailed assessment doesn't include the utilization as such, because there was too much uncertainties related to the amounts that could be addressed by this solution. However, CO2 utilization is still useful and could be seen also as a very good opportunity for revenue mechanisms for the full value chain. So to be able to define the transport and storage scenario, some workshops have been carried out, and we have also considered the different type of emitters that we had for each cluster. So it's interesting to note that depending on the cluster, so the industry sectors are different and could lead to different amounts of CO2 handled by the CCUS value chain. So for example, in Force Marseille, there are more like iron and steel associated emissions, are also linked to the power sector, while in Tarragona, emitters are mainly refineries or chemical plants. So this is quite important to note to quantify the CO2 emissions that could be handled by the value chain. So as I said, we carried out a workshop to identify and define different concepts for the transport and storage parts. During the assessment, which was done with all the partners, two cases stand out, and they were quite difficult to select between one or the other. So both cases have been looked at in terms of technical and economic assessment. On the left side, you can see the reference case, which is based on an onshore collection hub, meaning that all the CO2 which is captured is sent to a unique area, a hub, close to in the Tarragona area. And from this area, this location, all the CO2 is sent offshore to the storage site, so around 60 kilometers away, through one dense phase pipeline. For the alternative case, there is also the need for a collection hub, but this time offshore, meaning that all the CO2 from the Tarragona and Barcelona clusters are directly sent offshore by pipelines, and the CO2 coming from Fos Marseille, coming by ship, is this time offloaded on a floating storage and injection unit, which could be moored close to the storage sites. So this case would avoid having an onshore terminal at Tarragona and allow to send everything directly offshore. These two cases, so as I said, have been defined technically and also looked at in terms of cost estimates. Just wanted to share, but I won't go into details, some general schematics associated to the concepts. So as you can see on the left, you have the emitters side, where the CO2 is captured, then compressed and conditioned to allow its transport through an onshore pipeline, gas phase pipeline, and then the compression is needed to be able to send the CO2 up to the injection sites. And from the Force Marseille emissions, these are liquefied and transported by ship up to the Tarragona terminal. There would be a need for temporary storage to allow continuous injection of the CO2 while the CO2 is transported from the emitters to the terminal. For the storage site, I mentioned we have some very preliminary data, but that was the basis for the study. So looking at the Ebro Basin reservoir with a total storage capacity of around 20 million tons. So look, if we are considering an emission of 10 million tons per year, it means that the lifetime of the facility could be 20 years with the assumptions stated. For the alternative case, we have the same reservoir, so same assumptions, and this time, so no onshore terminal at Barcelona, but everything sent to the offshore location through a floating storage and injection unit and the offshore dense phase pipeline from Tarragona and Barcelona clusters. Barcelona being slightly further away from Tarragona, there is a need for a slightly bigger pipeline compared to Tarragona, also due to the difference in the volume to be transported. So this, in few words, is the technical definition. So there has been some preliminary equipment sizing, pipeline sizing, to be able then to do the cost estimates and the capex and opex assessments associated to both cases. The cost estimate accuracy is what we call a class 5 based on the AACE norms and is assuming a cost baseline end 2023. So numbers have been calculated using assumptions, as I said before, so to be used and considered with care, because there are many uncertainties associated to the data. But you can see, and that's quite an interesting outcome, that both cases show similar cost estimates, both in terms of capex and opex. A slight difference due slightly higher for the alternative case, but very, very minor compared to the accuracy of the estimates. And we have estimated a levelized cost of around 130 euro per ton of CO2 over the 20 years. Obviously, there are some exclusions to have in mind. So these numbers exclude the CO2 utilization plants. It also excludes some of the specific aspects related to transportation to sites, route survey or right-of-way, major harbor changes as well, decommissioning, etc. All the details are in the notes, but yeah, we need just to be careful that there are some additional costs that would be added when there will be a next phase, and we'll have more details on the different elements. Interesting to note the share between the capture and transport and storage in terms of cost, where we have around 45% associated to the capture and 55% for the transport and storage parts. And really, the economic viability of the concepts relies on on the capacity to transport as much as possible, as a largest volume of CO2 as possible, to amortize the high investment costs. And as you can see, this type of development would need support, external support, or external revenues to be able to be economically viable. Regarding CO2 utilization, so as I said, it has not been quantified in detail. However, there is a real interest to envisage this application and to be able to use common transport and storage infrastructure with the CCS value chain to minimize costs. And if there is availability of green hydrogen at an acceptable cost and biogenic CO2, there could be real opportunities for these applications. Okay, so I went quite quickly through the different points, but yeah, I think I need to go now to the risk aspects. All the details will be shared, obviously, in the reports at the end of the project. So to look at the risk assessments, basically this was done as a collaborative exercise with all the partners to be able to have a thorough analysis. So initially there was a categorization of the different risks, like environmental and social, safety, security, technical aspects, financial, business model, and legal and regulation topics. And looking at those categories, through a one-day workshop, we looked at each of the possible risks in a systematic manner, looking at possible causes, consequences, and quantifying the likelihood and severity of each of the risks. The idea was really to be able to assess if the risk had high score in terms of impacts, and then be able to focus on the most critical ones for later stage. For each of the risks, some mitigation measures were also defined and then compiled in a risk matrix with all the different details and assessments included. At the end, that allowed to have to identify either existing or new mitigation measures to be put in place, and also to highlight what are the most critical risks to be addressed to ensure a successful project development. So I've put here some, well, I would say a few of them, because actually the matrix is pretty long. On the non-technical aspects, and I guess with no big surprise, you have the environmental impact and leakage risks, which are seen as critical and also linked with the public perception and acceptance. So these should be addressed by detailing more the environmental impact assessment, how to address leak, how to define leak detection systems, etc., to make sure everything is done in a safe manner, and that would also help to reassure the public regarding the the safety and minimal impact of the development. Another one which is very important and includes different points is related to the regulation and government support uncertainty, as well as the revenue mechanism uncertainties, which can sometimes and often lead to the difficulties of investments and decisions, as investors don't have the a good vision of what's going to happen in many years' time. So stakeholders engagement is key, and also need to clarify all the regulations aspects and the definition of the business model to ensure that the project can go ahead and will find financial support. On the technical part, as of today and at this stage of project, which is very early, there are a number of technical risks associated to the uncertainties of the technical inputs, such as the amount of captured CO2, the transportation schemes definition, which for now are preliminary, and that would need to be further developed to confirm the feasibility and the technical and the cost associated to those. The maturity of the geological storage site is also a risk to be addressed, both for the Mediterranean part and the Baltic part. Some of the sites which have been identified are yet to be appraised. So yeah, further details and engagement with the storage site owners will be required to de-risk this point. Lastly, for the CO2 utilization, I mentioned it a few times, need to go into more detail to assess the technical and cost feasibility of those developments. So that's more or less what I wanted to share on the risk aspects. And I will now leave the floor to Leandro to share what has been done on the Baltic Sea region.
All right, thank you for the nice presentation, Audrey. I will share my screen now. All right, so I'll take forward with the Baltic Sea region. value chain, the selected one, doing firstly the same thing that Audrey did for Mediterranean, just to show what came before this selection. So we took the Mediterranean, the Baltic Sea region, and we tried to map the emission sources, the storage sites, potential transport infrastructure existing or identifying potential new solutions and utilization options. And by doing so, and also mapping the non-technical aspects of these countries regarding CCUS, we try to come up with concepts of potential CCUS value chains, and we achieved 4 of them. So one in Latvia, Lithuania, 2 of them are located in Germany, Denmark, and Sweden, a larger one and a smaller version of a similar type of value chain, and the last one in Poland. So the one that I will detail a bit further now is the larger one, the one located in Germany, Denmark, and Sweden. So let's go straight to it. The proposal here is to set forth a large-scale cross-border CCUS network. So 3 countries. We gathered up 33 meters overall, and we estimate that they will be able to capture close to 20 million tons of CO2 per year. Then the CO2 is distributed by 8 different geological storage sites that you see in pink in the map. And we have assumed more than 928 million tons of theoretical mean storage capacity. And this will translate into a yearly injection volume of 15 million tons per year. So this is lower than the 28 captured. So we need to close the balance with CCU. And we modeled 6 million tons of CO2 consumption for CCU installations. So this is in key numbers how we define our selected Baltic Sea region value chain. Then we connect the emitters to the sinks, storage and utilization, mostly by a pipeline infrastructure with the support of some shipping lines for offshore storage sites. All right, so now let's try to dive deep between each parts of the value chains first with the emitters. So initially, the only criteria that we have for mapping the emitters was emitters that had more than 100,000 tons of CO2 emission volumes per year. So we need to filter. The first step is to filter this this selection, and we try to use this value effort matrix prioritization technique. It consists of plotting the emitters in this graph, where in the y-axis we try to account for the value, and the value for us is the captured volume. So it's quantitative, so we can calculate this and easily put it on the plot. On the x-axis, though, we have something a little bit more qualitative. We call it the feasibility of capture. And it basically means a market assessment. So for each of the emitters, we try to look who had already plans to decarbonize through CCUS, who had different plans, who was going to retrofit to different kinds of fuels, who was going to close, who had good chances of investing in CCUS. And by doing so, we classify them between low, medium, or high feasibility of capture. And this way, we are able to plot the emitters in the graph. The next step is to draw 2 diagonals. The first one is the orange one, where we try to segregate the high value, high feasibility of capture emitters. So these are the ones that we'll be calling the front runners. So the phase 1 emitters that will set up a CCUS network. Then we draw a second green line with also a high value, medium feasibility of capture as well. And these are the followers. So the ones who we assume that will invest in CCUS once there is something already in the market. So there's already some maturity. So this graph allows us to provide both a schedule or a tentative of a schedule, and also to filter the emitters that are relevant for this analysis. And the results, so we can see more or less on this slide, we have 33 emitters. We have 20 million tons of CO2 captured per year if we assume a capture rate of 95%. And out of these 20 million tons, 8 are considered to come from biogenic sources. And just an important note here, the emissions that we mapped are from today, and most of them come from the power sector, and a lot of those come from fossil fuels. And we have assumed that many of these emitters will retrofit to biofuels, and thus the high value for biogenic captured CO2. So we are assuming that the capture will happen after this retrofit, which is not included in this technical analysis. Another thing to look at in this slide is the mapping of the emissions. And we see that the highest value is located mostly in the German clusters, Bremen, Hamburg, and Hanover, and also in Gothenburg in Sweden. So this is where we have the high volumes of CO2 being captured. But in Denmark, although we have smaller emitters, they are located closer to the storage sites. So we can just with this map say look at the feasibility of capture of these emitters is probably quite high. So this is one way to look at the previous plot that I showed, just looking at geographic distances and volumes. Right, we have selected our sources. Now let's move to our sinks. So we have both storage and utilization. Starting with storage, we selected 8 different storage sites. 5 are located offshore, 3 are located onshore. While we were doing this project, many of these storage sites were being developed already. So in parallel, and you can follow actually the storage licensing map that applied to some of these storage sites. So we actually have selected in the meantime 3 of the storage sites that have been awarded with a license to explore. This doesn't mean that they are already commercially viable and can operate, but they can be subject to appraisal now, and if appraised, they can move forward with their business case. So these 3 projects are Bifrost, Green Sand that received FID this week, and Gasum. Besides this, we have 4 storage sites that are either on with a tender for the license to explore, or the tender will come up sometime soon. Those are Ines, Lisa, and Jammerbucht offshore, and Torning onshore. So the only storage site that's not in this map is Voldum, that's located quite close to Gasum. And so we are assuming that if Gasum reaches appraisal, Voldum, which is assumed to be quite similar to Gasum, will also have a high chance to be successful. So these are our storage sites, but as I said before, they are able to store 15 million tons of CO2 per year, but we have 20 million captured. So we need to close the balance with CCU. And for that, we assumed 3 different hubs, where each hub has 5 CCU installations. 1 hub in Bremen, 1 in Aalborg, and 1 in Gothenburg. And they were selected in a way that the transportation system allows for a high flow rate of CO2 in these 3 locations. Therefore, these are the best locations for CCU plants to install, because they have different sources of CO2 coming up at high volumes. And they will consume 6 million tons of CO2 per year to produce methanol or synthetic jet fuel. Okay, now we have defined the emitters, we have defined the sinks. It's time to connect the dots. And we can talk about the transportation system in more or less 3 semi-independent systems. So the first one is located in Bremen, and it consists of sending the CO2 from 3 emitters straight to the utilization hub, because the emissions here match exactly the value required for utilization. And what I would like to highlight here, we have selected here a pipeline infrastructure for this connection. And it's a fixed infrastructure, okay, but you can see how, or you'll see in the next slide, how a pipeline can decomplexify the transportation system in terms of conditioning and in terms of infrastructure. So if we move to the next slide, here we'll see the transportation system block flow diagram for the German emitters and the Danish emitters. And it's mostly a pipeline system, but now we are also introducing shipping. And for shipping, we need additional conditioning, we need liquefaction, we need intermediate storage hubs, we need harbor retrofit loading stations, we need the ships. So we are adding a little bit more complexity, more flexibility as well, but also more cost. So there is advantages and disadvantages in these types of transportation. The final transportation system to show is located in Gothenburg. And Gothenburg is a bit tricky because it's difficult for pipelines to access the Gothenburg port. So the way we found out to transport the CO2 there was by either trucks or barges. And because of that, here we require a large number of liquefaction units, intermediate storage, loading station, and this makes this this arrangement much more flexible, okay, but also more expensive and much more complex. But okay, so this is how we define the transportation system for the Baltic value chain. Now we can look at the costs. And before looking at the numbers, just to show the scope of the cost estimation, we go from capture to the transport and storage. We are also taking into account the developer costs, so owner's engineering, from permitting, marketing, communication, surveys, and we also took a budget for contingencies for risks. But also very important to note in this cost estimation are the exclusions, and I would like to highlight two. One is the utilization costs. So we have projected 6 million tons of CO2 utilization per year, but we are not taking into account in this cost estimation. So this was excluded. The second thing that's also important to note is the heat and fuel for carbon capture plants. So each carbon capture project can be quite specific. We can have different sources of heat from the emitter current operations that could be redirect for the CO2 plant if needed. So we tried not to generalize, so we just excluded this part of the cost estimations. So the numbers that you'll see have a gap there. So, and that's important to note. So looking at the numbers, we have a capex of close to 21 billion euros for this whole value chain, and an opex of, when we reached phase 2 with all the emitters, close to 900 million euros per year. If we want to compare capex and opex, we can bring all the costs for the whole project duration, which was 30 years so from operation start, and bring it to present value. And that would be the net present cost, which is close to 13 billion euros, and the levelized cost of 168 euros per ton. Just be sure that when we are comparing these numbers with others that you can see in literature or other presentations, we need to be sure about the scope. So I try to note that we have important exclusions here that make this levelized cost maybe smaller than what it would actually be. And that's just important to not compare straight away with other projects. Two things about this slide more. So here you can see also the capex phasing that we talked about in emitter during the emitter selection. So there is a phase 1 where we built our infrastructure from 2030 to 2035, and then the second phase from 2040 to 2045. And finally, a note about how do we distribute the costs per work breakdown structure item. So in this pie chart, I have the net present cost divided by each item. Half of the costs are for capture. Here we are missing the heat and fuels. We have 20% for transportation. We set a quite high contingency budget because this project is so at an early phase that there are a lot of risks that we are not aware yet. So it's important at the beginning of a project to try to have this kind of assessment and understand what kind of budget would we require for risks. Then we have the storage 8%, and allowance, which is owner's costs, permitting, engineering 7%. Okay, so this was the technical and economical presentation about the Baltic value chain. Going back to something a little bit more generic and that scopes both the Mediterranean and the Baltic Sea regions. When we are defining a business case, there are several additional steps that we need to define. One of them is how to allocate responsibility throughout the value chain. So how to integrate different sections of the value chain. We are not making a specific recommendation, but we're mostly trying to identify what are the possibilities. The first one could be a full chain model. Basically, it's one integrated service provider that covers all sections of the value chain. Because of the size of both of our value chains, it might be quite difficult to implement this one, since it requires the involvement of so many stakeholders, so many disciplines, and very high financial support. So the next ones can be applied for as something like a multi or single or multi-hub integration model. The first one is the self-capture, where the emitter takes the responsibility to own and operate the carbon capture plant, and then the CO2 is off-taken by a third party. We have capture as a service, where the emitter hires an operator to own and operate the carbon capture plant, and this provider, they can offer their services to multiple emitters, so they can really specialize their offer here. And on the transportation and storage side, we can have TNS as a service, so different operators of taking the CO2 to the sink. And here it's also important maybe to distinguish between flexible kinds of transportation like trucks, barges, ships that allow for some kind of competition, or pipeline systems and fixed infrastructure, which the emitter may be quite relying on this infrastructure. So there may be a window for monopolies here, and this could require more or less involvement from the government to set some rules. Then a very important part of the business case is to define the stakeholders. And in our reports that I hope that you'll have the chance to read, we have identified specifically something like a yellow page where you can see who could be involved in these specific value chains. But here I have just a high-level categorization. First, the project developers and partners. So these can be the emitters, aggregators of CO2, or TNS operators. We also included support functions like consultancy and research who can help develop the project. On the regulatory authority side, we have the institutions that protect the nature considerations, water framework, cultural heritage, safety issues, health, and this can be national or EU level institutions. They can cover municipalities or local planning. Then we have the NGOs who are also very important. So they promote the clarity of understanding the challenges and possibilities of CCUS, and they can act both near the developers and the authorities to help them formulate an informed decision. And finally, the financial institutions. So they provide financial support, and they can be reached at national and EU levels. So some of these are more specifically identified in our reports. Finally, about the business case, to ensure that our business case is successful, we've talked about the costs, but we also need to ensure that there's some kind of predictable revenue stream which de-risks the project. And here we have identified multiple ways to define revenue. It can be by utilization of CO2 or selling it as a commodity, through carbon markets, voluntary or compliance markets like the ETS, by selling patent licenses of products related to CCUS. We can also sell a product that was obtained has a low carbon through CCUS with a higher premium. The government involvement can also be quite important, either as a direct subsidy or as owning part of the value chain, or as taxing CO2 emissions or providing incentives for avoided CO2. And finally, we can also have other services that are generated by the CCUS operations. For example, we can use waste heat for district heating and generate revenue like that. Consultancy and research will also need specialized competences that can be also a source of revenue. And MRV activities can also generate revenues. So to finalize, just some conclusions. We try to provide with these both value chains a suggestion of how to define a CCUS infrastructure at a large scale and provide viable paths for a business plan. But the results are obtained through very early premises. So there are uncertainties and risks or opportunities that could quickly change the project layout. And it's quite important to take that into account when we are looking at the how good is the business plan and how what is the risk level. Some of them are, for example, related to the geographic location. So in this project, we restricted ourselves to the Baltic and Mediterranean Sea regions. If we could import, for example, CO2 from other regions, or we could export CO2 to the Norwegian, Netherlands, UK storage sites. This was not included in the business plan formulation. But it would be one thing to think in real life. So we identify the main drivers to successfully deploy this business case. First one is de-risk technical challenges. So go through all the phases of engineering, feasibility, concept definition, concept freeze, pre-FEED, FEED to make a better informed FID. Then the stakeholder engagement, it's quite important that for such large networks that have impacts or require the support of different stakeholders, it's important to engage with them very early. And finally, to secure long-term and clear policy supports to make this CCUS business a little bit more predictable. And this includes fiscal incentives, carbon pricing, subsidies, and so on. All right. Thank you for staying with us so far. You will be able to see our deliverables or reports in our website, but you can also subscribe to our newsletter and social media. But for now, I'm happy to take questions. Thank you so much.
Thank you, Leandro, and thank you, Audrey. There's a few questions in the chat already, but in the meantime, I'll take an opportunity, since you mentioned the website, social media newsletter, to remind everyone that this webinar is being recorded, and we will be adding it to the website at a later stage, along with all the previous project webinars that you can also watch there. I'll take a moment to enable microphones and cameras for all participants. So just a reminder to please keep your microphones muted unless it's your turn to ask a question. And if you do want to ask a question, please use the hand raising button on Teams. There's a few questions that I noticed on cost, so I'll sort of read them out. They were asked, I'll mention this, they were asked towards the end of Audrey's talk, and I think Leandro might have addressed some of them. But if there's anything to add, please feel free to pitch in. I'll read them, three of them together, potentially a fourth one that came through as well, all related to cost, and then I'll let you guys address them in your answers. So first of all, it was how would you justify the underestimated cost, euros to ton of CO2 present in the literature, that is more around 200 to 250 euros per ton of CO2? The second question is, how would you justify the ratio cost between capture and transport and storage? Because there are other studies that showed the capture cost to be 70% of the total CCUS chain costs. And also there was a third question about also the ratio cost between storage and transport, and in general a question about costs of the identified for the Baltic area.
Thank you. We were expecting some questions on the cost, so that's very good. And I think, and Leandro, I will let you complete what I'm going to say, but the numbers, it's always very tricky to show numbers like this in just a few minutes without being able to detail all the how the cost has been built. We could spend an hour just to explain this. Yeah, I guess first the point is, are the battery limit of the cost similar? Maybe that's the first thing that maybe we should look at to compare the numbers. In our case and in our assessment, as we've said many times, I think that's very, very preliminary. Data available to do the assessments was limited in terms of I would say site data. So if I can take an example regarding the capture part, all the brownfield integration impacts of also the pipeline routing, many assumptions have been made to provide a high level estimates, and likely, as you are saying, underestimated compared to some other numbers. Assumptions are stated, they can be challenged definitely, and can be adapted depending on the real data that exists. But as part of the project, all the data was public, and we didn't have the opportunity to go through each of the emitters, looking at the real site aspects, etc. And same for the storage part. The only information that we had at hand, at least for the Mediterranean parts, were some high-level numbers, so related to all the details on injectivity, monitoring parts. Yeah, some costs could be added depending on the real the real behavior of the site, for example.
Mm-hmm. And maybe just to complement, I know that maybe 200 to 150 euros per ton is more realistic. One thing that these large scale projects, they can also mutualize some of the costs. So there is the opportunity of some economy of scale. But you're right that there's something missing there, and I talked about the lack of utilization in the cost estimation, and on the capture, the heat and fuels would take a big impact in the OPEX of the carbon capture sites. So there are gaps there. So these numbers that we share, they are clear. I hope in the report we have stated the assumptions and the references. So hopefully you'll be able to look at them and not just take the number directly to compare with the others, but see what's behind them. I don't know if we addressed all the comments. Yeah, about the ratio between storage and transport. I think I showed the pie chart in my slides where you can see that transport was around 21% of the net present costs, and storage was around 8. But it's also important to understand that this is still very early stage numbers. So the most important for us in this project was not to was to show, of course, the realistic values, but mostly to show how to define or what to define when trying to come up with a business case or a technical definition of a project of this dimension. I think you're muted, Richard.
Thank you both. Yeah, thanks for the answers. There's also a question about how is the risk of seismicity and high concentration CO2 leakages, how are they assessed?
Yeah, this is something highly the storage sites in the Baltic region, at least they are a lot of them were sent for appraisal, and even during appraisal things might happen. Even during operation, there's the events can happen that maybe either reduce the injection capacity, for example. So one of the things that we identified in the value chains is that on the storage side, we are very exposed to storage risks. So, and if there is a reduction of CO2 storage in the Baltic area, then we have a big problem in terms of demand, because so we have 20 million tons of CO2 captured, 15 stored, 6 utilized. So we have 21 million tons for sink. So there's only a gap of 1 million ton between the capture and the storage. And if a storage site is removed from the map, then this 1 million tons is not a pillow large enough to take that. So it's important to de-risk by looking at other geographies, but also, as Audrey said, going through the proper engineering steps to correctly define this storage sites and appropriate mitigation measures of risks like the one that you mentioned.
Thank you, Leandro. I think that's the questions on the Q&A. You can still submit any other questions, and a reminder that you can also raise your hand if you'd like to ask a question verbally. So I'll give another minute for people to decide whether we want to ask a question. Any additional ones? Yes, we have Cesare. Hoping I'm pronouncing that correctly. There was a hand up. I think it's just gone down again. Yes, there you are.
Thank you very much for replying to the questions, and the presentation was really clear and super interesting, actually, for both areas. Just I didn't understand the reply to the question on assessing the seismicity and eventual surface back leakages of the CO2 injected. Maybe I missed something, but I didn't understand how the issues will be or has been, I don't know, interpreted or assessed.
My answer was trying to agree with you, and that we are very exposed to this risk, and we have project restrictions that, for example, don't allow us to look at de-risk this by looking at different geographies, for example, because but regarding the specific how do we praise a CO2 storage regarding the seismicity risks, we did not look at this into detail. So we have assumed that the storage sites, if they are all appraised basically, and we developed this risk register that you'll see in our reports, where risks related to storage are actually quite high on the red zone in the matrix that Audrey presented. So they are identified, and some potential mitigations are shown in terms of engineering steps, but since it's a early stage project with a lack of a lot of information, that's the only thing that we can do: identify and flag it.
Yeah, and I think it's and in the Spanish area, there has been some past history related to some issues on the reservoir. So yeah, it is definitely a high risk, and it's part of the scope of the future storage owners and operators to go into the detailed geophysics assessments, reservoir assessments on all of the aspects. Yeah, but yeah, it is a very big, very important topic to highlight and mitigate. Yeah.
Thank you.
Amazing. Thank you very much. And once again, thank you to Audrey and Leandro. I think that's time for the webinar. We're coming to an end. Leandro and Audrey, I also want to invite you to have a look at the chat. There's a quick thank you and invitation to connect by someone on there, connect via LinkedIn and so on. But yes, so once again, the webinar recording will be available on the website along with the presentation slides. So all that's left for me to say for now is once again, thank you to Audrey and Leandro for the presentations. Thanks for everyone for attending today. And we hope to connect with you via our social media channels. Keep an eye on our website, register for our newsletter, and stay tuned for reports and more recent updates on the project. So thank you once again.
Thank you.
Thank you.
Thank you so much. Bye bye.